When considering flows in open channels, there are two main assumptions that help us to find simpler solutions than we would in the general case in which flows can accelerate both in space and in time. And we call those two special cases that of being steady, meaning that there are no accelerations in time, and these are the normal accelerations we're used to talking about, and uniform, meaning that there are no accelerations in space. And I'm going to describe that a little bit more down below. These two assumptions help to greatly simplify the mathematics, and they're actually applicable in a wide range of natural environments. And so let's just go through these and talk a little bit more about what they mean. So as I mentioned, a flow that is steady is not changing in time. Let's see if I can underline that. There we go. And what does this mean? This means that all the time derivatives are set to 0, right? So if it's not changing in time, anything that's dt has to go to 0. And x is just a dummy variable, and so x could be something like, velocity, mean velocity of the flow. So in this case, we'd actually be talking about true acceleration, right? If you're talking about change in velocity over change in time. But most importantly, there are no accelerations, right? And so that's what I was just mentioning. So no changes in velocity over change in time. And one thing we can think about is that actually, strictly speaking, this isn't true. So if I'm actually standing at one point in a river, let's say at a bridge, and I'm looking down at that stream, and as I look down and I pick a point inside that stream and just go through time lapse and go from a base flow, so just being fed by groundwater, low flow, to a big flood. During the flood, the velocity is going to increase. But the point is that it takes a long time for that velocity to change. And the amount of time that it takes for water to travel through a reach of the river is much greater than the amount of time that it takes for the flow to actually change from a standard low flow condition to a flood condition. There are exceptions that exist to this rule, of course. And so there's, for example, let's say there's a really big flood wave, like earlier this year as I'm recording in 2020, there was a dam breach in Michigan that led to a really catastrophic giant flood wave. And that is moving fast, and that is going to present a wall of water in which we actually do have to think about these accelerations. But in general, for your normal everyday garden variety river, you don't have to worry about this too much. And fortunately, there are some really bright hydraulic engineers who also think about the flood wave problem and help to work to design better structures and better hazard management plans. So for this uncommon situation of a dam break, though, let's think about that. So what we have here is we have a big wall of water that was impounded behind a dam, and now the dam is saying goodbye. And here we are. Let's just... And so downstream, there is... I'd better actually draw this, sloping downwards. So this is the river. And so this is at something like at time 1. And at time 2, what you can imagine is that this flood wave is both advecting downstream and it's dispersing. So it's getting a little bit wider, but there is still a pretty big shock front that's reaching this downstream area. And so this is, just to remind you that this is not normal. And it's definitely not steady. And it's also probably not uniform. So if you think about stuff like this is not what we're going to be solving with these equations that we talk about in this class. If you're really into this, go take a hydraulics course in civil engineering and you're going to learn all about this. There's actually some really great hydrological design classes that are taught right here at the University of Minnesota, and you're going to learn all about dams and how to manage hydraulic structures. So the other assumption that we make is that flow is uniform. And what does that mean? It means that flows are not changing in space downstream. And therefore, for any quantity and some sort of downstream oriented spatial dimension, x, we have all these d dx's equals 0. And so, for example, what that means is that the flow going through a section of river that I'm standing in is moving, for example, if we're thinking about x again as velocity, as let's say mean velocity. So if I'm standing in a river at one point here, then up to my waist in the water, have a little triangle symbol showing that it's water, is that my friend downstream, and will make my friend be a gray person, is experiencing the exact same velocity, right? So both of us are feeling the same u bar. We go and measure it, it checks out, and it's uniform. If my friend, for example, were feeling a slower or a faster velocity, then the flow would be non-uniform, and we would have to start to think about situations in which non-uniform flow might start to matter. And actually, that's important here. So when considering these sorts of natural flows, there's a common case of non-uniform flow when a river approaches a lake or ocean. I'm going to put these two together. So these are a body of standing water. Or a waterfall. And so we're just going to put this up here as some kind of edge or like a free surface. And so this is a zone where there's going to be spatial acceleration as opposed to the more common temporal acceleration that we think about, that we usually just call acceleration. And in this case, if you're following along a single water molecule, it is speeding up in time. But if you're standing still and looking at one point, you actually notice that acceleration is happening in space. So let's just sketch a few examples of how this might play out. So I'm going to start out with the first example of a river, and then eventually there's flow into a lake. And at the lake, there is some sort of water surface that is marked right there. And then as we go upstream in the river, that water surface is actually exerting a pressure force. That is affecting the flow upstream of it. And so let me just try to draw this sort of gradually shallowing line. Maybe it's going to be easier for me to draw upstream to downstream. My artistic skills are not so great right now. But what you might be able to imagine is that there's a point at which, all right, we're going to try a little harder here. Slow and steady. All right, pretend that's all kind of steady, and so that there's a point at which it's getting deeper, and so gradually approaching this edge of the lake. So over here, flow gradients are decreasing, and the flow is getting deeper because there's a backwater effect. And then here we have velocity that's fast, and down here we have velocities that are not quite so fast. So flow slowing down. The other example, of course, that we can talk about is this waterfall. So let's hope I can draw that a little bit better. And by the way, just to maybe zoom in on this spot where I wasn't drawing it very well, let's just say this zone right here. Let's just draw this in a much more schematic way. We have a slope right there, and then that's going into this body of standing water right here. And so what's happening is the water surface of the river is starting to go like this as entering that standing water. Meanwhile, the bed might be continuing to go down like that. And so this actually is a much better drawing of what we would call the backwater zone. And so that's where these pressure forces start becoming important. And whereas up here, we really just have gravity pulling the water downstream. So there's just density, gravity, And so it's basically just the mass of the water kind of flowing down the slope. If all this stuff is actually sounding a little bit like I'm jumping ahead, that's okay. I'm just introducing a few terms. We're going to get back to them in the next several videos. So the other example that I was starting to mention is a waterfall. So waterfall, let's just draw a nice riverbed like this, and then the whole thing falls off an edge. What happens here is that if there's a flowing stream, that flow is actually accelerating and getting thinner because there's nothing here to push back, right? So you can say, if, for example, here there's this extra pressure force, but here there's nothing pushing it back, so the flow is actually then thinning and getting faster. So we go from a velocity that's slower to a velocity that's much faster out here. And so this is the waterfall example. And so both of these are examples of how spatial acceleration can happen. And I'm discussing them because they're important in nature, but we're mostly not going to consider them because dealing with the mathematics here is going to be too complicated for trying to have a general geomorphology class in which we can cover a number of different topics. But we might want to consider when, at least when these things might be important versus when we don't have to worry about them. Because then we at least can know and we can be certain when the simpler approaches I'm going to present here can be used. And to do so, we can create a scaling relationship that we call a backwater length. And so this right here, this backwater length, is a ratio between the depth of the flow and slope. And what this is it's the distance over which the channel becomes one channel depth higher in elevation than the boundary producing the backwater. And so the idea is that once the channel is one full depth above itself, so let's say that this is the channel right there, and then if the channel is then, if we go far enough upstream that we can create a view of the channel being one channel depth above itself like this, that distance upstream is going to be the backwater length. And so here, what you can imagine then is that this is going to tell us, well, I guess you can do more than just imagine. I mean, you can see that this is just going to tell us for a certain kind of river how far away from a backwater it might that the backwater effect might matter. So let's take a couple examples. So the first example I have here is a gravel bed river approaching a waterfall. And so right here, we have a riverbed, again, doing that, and then it goes off over this waterfall. We have this accelerating flow and then shoots off the edge right there and starts to tumble down. And we're going to just use our example, Minnehaha Creek in Minneapolis, which is a gravel bed stream. And let's say that this bankful depth of the river is about 1 meter. So, and that's the depth at which it fills its fills its channel to the banks, and it's just on the very edge of flowing over onto the floodplain. And we're also going to say that the slope of this channel is 10 meters per kilometer, so 0.01. And so if I create a backwater length, and we can look up here, check this out again, so length of the backwater is depth over slope. And that means that this is 100 meters. And so if you're able to go to Minnehaha Creek or a similar waterfall and think about what kind of distance you might see the water start to look like it's streaming and accelerating, that distance just might be something around 100 meters if the water has the depth and slope that Minnehaha Creek does. And what you can see here is that you might expect that if the water is shallower, it's not going to feel that edge as far upstream, or if the flow is steeper, it won't feel that edge as far upstream. So let's take a second example. So this one is about the Mississippi River, and so we'll have this yellow bed, You can't really see that. All right, gray bed. For this big sandy Mississippi River reaching the ocean and the edge of the continental shelf. And we have the river water surface over here, and then it kind of flows off like this to merge with the ocean. And so the question is, how far upstream is it feeling that backwater effect? And so the depth here is closer to 10 meters, and the slope is closer to 10 to the minus fourth. So we have 10 to the 1 over 10 to the minus 4 equals length of the backwater. And so 10 to the 1 over 10 to the minus 4 is equal to 10 to the 5 meters, which is equal to 10 to the 2 kilometers. So what that's telling us now is that 100 kilometers upstream, so pretty far upstream into Louisiana, we are still going to expect to see, if these parameters that we chose are correct, a significant effect of the back pressure of the Gulf of Mexico on the flow in the Mississippi River. And so that starts to become really significant. And so the big deal here, one of the big takeaways, is that the backwater is important in low gradient, large, lowland rivers. So as a result here, we're going to talk a lot more about smaller upland streams. And that's fine, that's fair for a lot of the rivers on Earth. But I just want you to know that there are limitations to the analyses that we're going to discuss here, and that if you want to start thinking about systems that are starting to approach the ocean, you might have to start thinking about some more advanced physics than we're going to present in this course.